Good day, viewers. I'm creating these videos to support teachers of mathematics to help learners make sense of mathematical ideas and their underlying processes and procedures. And today what I want to look at is simplifying sums and differences of algebraic expressions by collecting like terms. Now, how I visualize and make sense of these expressions very much comes down to how I choose to make sense of the numbers and variables that are used within these expressions. And broadly speaking, there are two ways I can make sense of expressions and values in a sort of concrete way. I can look at them as continuous, so I can see them as lengths, areas, potentially even volumes. Or I can look at them as discrete. I can view each separate term or expression or variable as a discrete little object in and of itself. And depending on how you view these depends on how the simplification of these sorts of expressions may look. So we're going to start off with a relatively simple expression, 3x plus 1 plus 2x plus 2. And over here, I'm going to build this expression using algebra tiles. So here I have my x's, and I have 3x's plus 1. And then I'm going to have another 2x's, and then plus 2. Okay, and normally I wouldn't allow that to overlap there. On a bigger screen it wouldn't, but it's not necessarily a problem that it does. So I am adding these expressions together, and that means what I'm doing is I'm connecting them up end to end, and that's what addition looks like in this situation. I'm connecting them up end to end, so I can see my 3x plus 1, and then connected to that I can see my 2x plus 2. Okay, and so how do I simplify this expression? Well, I simplify this expression, or I can make sense of simplifying this expression by thinking, well, that whole expression is a length in itself, but were I to rearrange these terms so that all the x's were connected and all the 1's were connected, I can do that without changing the overall length of the expression. So I can move things around in this expression without changing the overall length. And so what do I have now? Well, clearly now I have 5 x's and then I have 3 1's. So the simplest form of that expression, having collected the like terms, is 5x plus 3. And I can do similar things with multiple variables. So I could say, let's have 3x plus y plus x plus 2y. And I can do exactly the same thing, as I'm sure you can appreciate. The only issue here is that some of the concrete sets of this manipulative of algebra tiles only contain the one variable. And if that's the case, then obviously pupils won't be able to manipulate two variables in this way, but they will be able to see it at least on a screen such as this, or make sense of it in a similar way. So here we are. I'm just about to finish building my expression. 3x plus y plus x plus 2y. And again, the idea here is, well, I can move these things around without changing the overall length of the expression. So if I move that y out and move the x across, I can put the y back in there, and I can see that I haven't changed the overall length of that expression. So the length of the expression represents its total value, if you like. And so now I've got 4 x's in a line plus 3y's. Okay, and I don't have to do this just with length, I can do it with area as well. So I could show the same thing rather as a length of 3x. I could show it as an area of 3x plus an area of y. And then I have another area of x plus an area of 2y. And I can recombine these without changing the overall area, although obviously if we're going to work in this way, pupils need to be clear that me dragging this down here hasn't changed the overall area of space that I'm covering. And similarly, putting these in here hasn't changed the overall area that I am covering. And I can see I'm covering an area that has a total of 4x plus 3y. And I can do similar things either with length or area with negatives. So I could say, let's for example have 2x minus y plus 1 plus another x plus another couple of 1's. Can add a y in there and then maybe put in a few negative 1's. There we are. So the expression I've got all together here is 2x plus 1, sorry, wrong, minus y. Let's correct that. Minus y first. Plus 1 plus x plus 2 plus y minus 4. And again, I can recombine all of this without changing the overall length of the expression. So I could bring my x across. I can bring my y's across. And I can move my 1's together, and I haven't changed the overall length of the expression if it's a length view we're using here. Now, of course, although I haven't changed the overall length of the expression, what I have got now is I've got some parts of this that have a length of 0, have a combined length of 0. And of course, to recognize that, pupils will need to be familiar with the idea of 0 pairs. So this y and this negative y have a total length of 0. So actually I could combine those and ignore that. Similarly, this 1 and this 1 have a combined length of 0. This 1 and this negative 1 have a combined length of 0. This 1 and this negative 1 have a combined length of 0. So the actual length of that expression just looks like that, because all the stuff that I removed already had a length of 0. And again, we've got to be careful with learners there. They've got to be really comfortable with the idea of making those 0 pairs in order for them to see that this is the same length as the thing I had before. All of those missing bits had a length of 0, so weren't contributing anything to the overall length of this expression. But then we can see that if we're happy with that the result is simply that I have 3 x's, I have no y's remaining, but I do have a negative 1. Now, of course, with the algebra tiles, if you've only got sort of the 1 variable algebra tiles or even 2, it's slightly more difficult to work with expressions with multiple variables. And also that you'll see here that although we could build expressions with squares, and obviously to build expressions with squares, I am going to have to take an area view here. So I could say build the expression x squared plus 2x plus another 2x squared is all I meant to build there. 2x squared minus 5x, and look at the area of that and see that if I bring these out, then I can bring these together. So in total having 3x squared, and then I can put my 2x's next to my 5 negative x's. But again, part of this is contributing 0 to its overall length. So this and that contribute 0. That contributes 0. So in effect, the length that I have is that length, 3x squared minus 3x. And of course, we get around the idea here of 3x squared minus 3x ending up being 0, because we can clearly see that we're not going to be able to zero pair those. But if I want to work with cubes, or if I want to work with multiple variables, this is a little bit trickier. I can't really extend this into 3D using algebra tiles. But if pupils are happy with those sorts of ideas, then I could move on to using algebra discs. And in a typical set of algebra discs, not only have you got your 1's, your x's, and your y's if you don't have algebra tiles with those, but we also have a disc for x cubed and the disc for xy, the product of x and y. And in a typical set of algebra discs, that's what you would have. Okay, but even if we don't use the actual algebra disc, if we use the virtual manipulative, if we want to work with other variables, I can, of course, change the values of these. So I can start working with j's. Now I can do that here as well. I can change the values on this one. So again, if I'm modeling this to learners from my board or remotely, then I can change variables around in here as well. This just gives me slightly more variables I can play with, and also allows me to play with cubes. You'll notice that although I changed the x variable to j there, it didn't change the x squared variable to j squared. So if I want that to be j squared, I'm going to have to put that in. But I can now bring in cubes as well, or I could change this to a different variable entirely. I could change this to p. So that gives perhaps a little bit more flexibility if you're working with expressions with many different variables, although of course one would hope that by the time they're working with expressions with 4 or 5 different variables in, pupils are perhaps starting to move away from needing these concrete or visual manipulatives to support that sense making. They'll be able to visualize that directly from the symbolic algebra. So that's just a quick look at simplifying algebraic expressions, but in particular the sums and differences of algebraic expressions, by collecting like terms. As always, I'd like to thank mathspot.com and its creator, Jonathan Hall, for the excellent website where you can find all these virtual manipulatives. If you've not been to mathspot.com before now, then it's very much worth going on and having a look. There is a huge amount of there for teachers of maths, not just the manipulatives that I've been using and other examples of other manipulatives, but all sorts of question generators and things like that on that site. It really is a treasure trove, so I encourage you to go and explore that. And of course, as always, if you're interested in looking at manipulatives and visuals, then I would encourage you to go across to my website, visiblemaths.co.uk, and amongst the many things you will find on that website, you will find a link to my book, Visible Maths, and you'll be able to go to the publisher's website where you can see samples and place an order. If there are any particular ideas that you would like me to look at, mathematical ideas that you'd like me to look at for using manipulatives and visuals to support sense making, then please do get in touch, because I'm aiming to carry on producing these videos all through lockdown. So please do get in touch if there's a particular one you would want to see. Thank you very much.